This is the story behind the electronics equipment that makes it possible for the Air Force's jet interceptors to seek out an enemy bomber day or night, despite the weather, and to attack and destroy the bomber without even seeing it long before it reaches our centers of population. Thus, it is the story behind our first line of defense against the airborne H-bomb. Also, it is the story of how, to develop and build this equipment for the Air Force, a small aircraft company grew into one of the nation's largest electronics producers, the Hughes Aircraft Company of today. The story begins in 1935 with a famous airplane, the H-1, in which Howard Hughes set the world's land plane speed record and a transcontinental record which stood for nearly a decade. This, incidentally, was a plane whose influence may be seen in every airplane that flies today. In 1935, it was the first plane to have a smooth metal skin, the first to employ jet thrust exhaust, power-driven retractable landing gear, bell cowlings, and several other innovations that are now commonplace. Overshadowed by the company's aircraft projects, the XF-11 photographic reconnaissance plane and the X-8-47 saw the first post-war development of the still small Hughes electronics department, an airline radar which would warn a pilot when his aircraft approached a dangerous obstacle. Then, in 1948, the small and relatively inexperienced Hughes Aircraft Company entered a bid in competition with the nation's largest electronics manufacturers for the development of an electronic system for the Air Force's brand new jet interceptors. This system was urgently needed. The striking ranges of strategic bombers had increased alarmingly. For the first time in history, the United States was subject to large-scale bombing raids, like those that devastated London and Berlin during World War II. Moreover, modern bombers could be expected to take every advantage of the cover of darkness and adverse weather. The electronic system which the Air Force needed for its new interceptors had to be able to detect a bomber at long ranges by radar and to direct the interceptor on an attack course for firing on and destroying its unseen target. Of all the highly competitive bidders, the Hughes Aircraft Company was the only one which said it could develop and build a flight model of the system in a year. Other companies said it would take at least double that time. To the surprise of the electronics industry, Hughes won the contract. However, 5 months after the contract was signed, the international situation became more critical. The company received a letter from the Air Force asking in substance, "In view of the present military crisis, how fast can you get your system into volume production? Can you give us a flight test in 4 months, a prototype system 3 months later, and production in another 3 months?" This was the moment for decisions. The major problems were these. First, did the company's engineers dare to cut 3 months off original contract deadlines? Second, would Howard Hughes agree to put up the millions of dollars necessary to build and expand plant facilities, to buy extensive new machinery and equipment? And third, did the company dare promise not only a very early flight test date, but large-scale production of these extremely complex electronic systems? In each case, the decision was yes. The following months were tense. Problem after problem had to be solved in this new field of aviation electronics as deadlines loomed. But the flight test schedule was met, and the production schedule was beaten by 2 full days. Then, a few months later,
"Your attention, please. Today, at the Air Force Proving Ground at Eglin Field, an F-94 jet interceptor equipped with the new Hughes electronic system shot down a drone target on an attack made entirely by radar.
Here is the system which the company developed. And here are the airplanes into which it went, early models of the F-89 and F-94 interceptors. Since those tense days in 1948, The Hughes Aircraft Company has developed and manufactured the electronic system for every all-weather interceptor of the United States and Canadian Air Forces. The F-86D Sabre, the F-89D Scorpion, the F-94C Starfire, the Canadian CF-100 Mark III and Mark IV, and for the United States Navy's F-2H-4 and F-3H-2N. The electronic systems that have been developed for the newer interceptors bear little resemblance to that first system of 1948. Before seeing what they're like, however, let's take a look at the evolution of the all-weather interceptor and at the problems of shooting down an enemy plane. Back in World War I, a pilot used a ring and bead sight to train his fixed guns on an enemy plane. Then in World War II, an optical sight was developed which permitted the pilot to move his head without destroying the accuracy of his sighting. Later, a computing gun sight helped the pilot calculate the amount to lead his target. The development of radar made practical the night fighter of World War II, for radar could find the target and assist the pilot in closing on the enemy to attack range. From the night fighter, the all-weather interceptor was developed. Like the fighters that preceded them, the first all-weather interceptors of our Air Force were equipped with fixed guns. But for interceptor use, fixed guns have serious drawbacks. An interceptor's guns must be trained on a bomber for a considerable time in order to damage it critically. To accomplish this, the interceptor must fly a curved course that draws it into the bomber's tail. The tail guns of a modern bomber, however, are so deadly that the interceptor has little chance of surviving long enough to shoot down the bomber. By 1949, a potent new interceptor armament had been developed: air-to-air rockets. One rocket contains enough high explosive to knock down a bomber, and a salvo of rockets can be fired in a fraction of a second. Thus, a rocket-carrying interceptor need be in a firing position for only an instant. This means that it can attack on a straight-line course from the side, forcing the bomber to fire into a terrific crosswind at a difficult target. These handicaps are so severe that the rocket-firing interceptor attacking from the side is almost entirely safe from the bomber's guns. Let's take a look at what the electronic system for a modern rocket-bearing interceptor does. The system for the F-86D, for example, performs three jobs. First, it locates the target at long ranges, day or night, and in any kind of weather. Second, it automatically flies the interceptor on a straight line attack course. Third, it automatically fires the interceptor's rockets at precisely the right time to strike the target. The electronic system for the F-86D basically is made up of a radar and radar scope, a computer, and a control surface tie-in. The radar serves as the eyes of the system. It sends out through its antenna radio frequency energy which is reflected by any object in its path. The reflected energy is received by the radar and sent to the scope, where it appears as a spot of light called a blip. The location of the blip tells the direction and range of the object. As the interceptor flies out to meet its target, the antenna automatically scans the region ahead, and the locations of all objects within the radar's range are indicated on the scope, shown here on the right. When the pilot locates his target, he stops this scanning, manually locks the radar on the target, and the attack begins. The radar now tracks the target and furnishes the computer with the target's position and velocity relative to the interceptor. From these, the computer continuously calculates the steering corrections that must be made to put the interceptor on a straight line course for attacking the target. Electrical signals calling for these steering corrections go to the control surface tie-in equipment, which automatically moves the aircraft's control surfaces so as to put the interceptor precisely on the computed course. So that the pilot can see the correct time, the computer automatically fires the rockets and a big X, and that he must take over and fly manually. Now that we have seen what the electronic system does, let's see how the mission of the all-weather interceptor would be carried out. This is one of the bases of our Air Defense Command. It is manned by an all-weather interceptor squadron whose code name is Overtone.
Well, here we are with 70,000 rapid fans for the postseason playoffs of the Senators and the Chiefs. The Senators are
These are the pilots.
the ball around, and we're set for a great game between top teams who have added to the dignity and good sportsmanship of professional football.
And this is the ground crew. If attack should come, this is what would happen. Today, the Hughes Aircraft Company, developer and manufacturer of the electronic system whose operation you have just watched, is one of the largest producers of airborne military electronics equipment in the United States. Its people and facilities occupy 72 acres of floor space. In its manufacturing areas, more than 8,000 interceptor electronic systems have been produced, each with as many as 17,000 separate parts. To design new and more advanced electronic systems for the interceptors of the future, the company's research and development divisions have grown till they now employ more than 5,000 people, some 2,000 of whom are scientists and engineers. More than 100 of these are PhDs, and more than 600 have master's degrees. These people, skilled in such fields as microwaves, antennas, miniaturization, semiconductors, electron tubes, and digital computers, are developing considerably more advanced electronic systems than the ones we have just seen. Some of these new systems will automatically navigate and fly an interceptor from the moment it leaves the ground until it returns to its base. Equally significant, some systems will fire a new type of armament, the Falcon air-to-air guided missile. The Falcon guided missile was also developed by the Hughes Aircraft Company and is currently being manufactured by the company at an Air Force plant in Tucson, Arizona. The Falcon will be an important air-to-air armament of the Air Defense Command. It contains a highly explosive charge and is small enough to be carried in quantities by almost any interceptor. Electronic equipment in the missile, seen here on a field checkout stand, enables the Falcon to see its target and to steer itself to correct its trajectory errors. As a result, it can be launched from far beyond the range of a bomber's defensive armament, and it can hit the bomber despite any evasive maneuvers. For these test firings, the explosive charge was removed from the missiles. Nonetheless, damage to the drone targets was severe, and frequently the drones were brought down by the unarmed missiles. For firing Falcon missiles, the new electronic systems being developed for the all-weather interceptor will perform the same basic functions as for firing rockets. Locate the target by radar, fly the interceptor on a straight line course for attacking it, and
In the beginning, the Douglas team was only a handful of workers, but in 1924, the name of Douglas was firmly implanted in the field of aviation. For in that year, Douglas planes made aviation history by completing the first flight around the world. Hundreds of people were at the airport to commend the pilots and the Douglas Aircraft Company. Some of the most noted figures of the day also cheered the event and personally congratulated the pilots.
pictures you just seen represent milestones in the Douglas Company history. You're going to become part of this tradition yourself. Welcome to Douglas. I'm what some of you might call an old-timer, like this Douglas World Cruiser. I can remember that first round-the-world flight. I even remember when the first Cloudster took off. I was pretty young, though. But, well, I'm getting a little ahead of my story. First, I want you to meet a man who, most of his life, has been an important part of the Douglas tradition. He's now the president of the company, Mr. Donald Douglas, Jr.
I want to welcome you to our organization. When I say we're glad to have you with us, I'm speaking not only for my father and myself, but for all of the men and women of the Douglas organization. We believe you'd like to know something of the history and the many products of our company.
As you can see, our den is full of Douglas history and achievements. As any old-timer will tell you, the Douglas story is exciting and it's fun to talk about. It's a story that spans the history of aviation from jennies to jets. It's a story lived by men and women, many of whom are still with us, who, well, remember the drawing board operation in the back room of a small barber shop in Los Angeles. A sharp contrast to our present complex of production, service, and design facilities. Equally vivid are the memories recalled by this picture of the Cloudster, the first Douglas airplane. Looks kind of odd, old-fashioned now, doesn't it? But poised out there on the end of that bumpy dirt runway, with the prop spinning and the smell of hot castor oil and wet grass heavy in the early morning July sunshine, she looked fine, real fine. She looked particular. Well, it did. And a new era was born, in which Douglas-built planes were to carry more payload, farther, faster, longer, and for less operating cost than any other. In 1924, these world cruisers, built by Douglas for the Army, flew around the world, covering 28,900 miles, an unheard of feat in those days. They proved the soundness of the Douglas design. The illustrious Douglas Commercial, or DC series of airplanes, began with the DC-1. Within a few months after its initial flight in 1932, the DC-1 broke 19 American and world records for transport aircraft. With the DC-3, commercial aviation came of age. No aircraft in history has earned a greater reputation for dependable service than this universally famous 21-passenger transport. Douglas produced 11,000 of them. Workhorse of the airlines, thousands of DC-3s are still in commercial service. Yes, those were some of the big events of the 20s and 30s. It all began in the back room of a barber shop with one man's dream. The Long Beach Division in California, built during the winter of 1940 and 1941. In 1942, demand for World War II aircraft carried Douglas expansion to Tulsa, Oklahoma. The most recent addition to the Douglas family was a division in Charlotte, North Carolina. The exteriors of our 5 plants may look much like any other factory, but inside, man's most recent dreams are coming to life. Luxurious ocean-spanning transports, carrier-based bombers, air-to-air and ground-to-air missiles, gigantic ballistic missiles. But I'm getting ahead of my story again. There was World War II. Douglas aircraft earned an enviable record during that war. Among the combat veterans was the Havoc A-20 light bomber. This same military version of the DC-3, the indestructible C-47, the most honored airplane in its class. Big brother to the C-47 was the C-54 Skymaster, the airplane that inaugurated the age of transocean flight and laid the foundation of modern global aviation. In all, the combined Douglas divisions built 29,385 of the airplanes produced during World War II. Their total gross weight was 216,000 tons, 1/6 of the total American output by weight, and perhaps 1/3 of the total number. For the Navy, A-3D and A-4D Sky Warrior carrier-based jet bombers were produced. Then came a Lightning. For the Air Force, B-47 bombers were produced under contract to Boeing. Additional wings for the Air Force include B-66 and RB-66 light jet bombers and reconnaissance aircraft. Also from the production lines of Douglas roll the mighty weightlifters, C-124 Globemasters, and now the C-133 turboprop transports, the giant Cargo Masters. With these aircraft, the military are proving out some of their new strategic concepts. For example, the C-133A is capable of airlifting any of the Air Force's IRBM and ICBM missiles, as well as the necessary ground support equipment. To keep abreast of the rapidly changing times, Douglas continuously maintains an extensive program of experimental development. Out of such development came aircraft ahead of their time. Aircraft like the supersonic Skystreak, the Sky Rocket, and the needle things are going on. New missile and airplane projects for the defense of America today. Research and development that will assure continued leadership for tomorrow. Probably never before in the history of this nation have major events of international scope created such a sense of urgency in our national defense planning. Almost overnight, the possession and accelerated production of modern weapon systems became the overwhelming concern of our government and people. In this new planning, missiles assume a greater and greater role. Douglas has had a long and successful background in the missile field, dating from 1941. Today we are producing missiles like Genie, an air-to-air rocket carrying a nuclear warhead, capable of destroying many enemy bombers in a single shot, with the equivalent of thousands of tons of TNT. Also in the air-to-air category is the Sparrow II, an advanced missile for the Navy. The Army's Honest John, an artillery rocket capable of using either a conventional or nuclear warhead, is another Douglas product. Douglas is also delivering to the Army the Nike family of air defense missiles, the Ajax, the longer-range Hercules, and the mighty Zeus. Batteries of Nike missiles have been guarding our cities for several years. A highly publicized missile for the Air Force is the Thor IRBM. This 1,500 nautical mile ballistic vehicle was test-fired many times at Cape Canaveral and is now in operational use at overseas bases. Thor is also most dependable as the prime power package for advanced long-range ballistic missile re-entry test projects, and as the powerful first stage that propelled the Air Force space probe Pioneer. Douglas has achieved the most varied experience over the longest period of time in all of the missiles industry. Douglas is the only American manufacturer to have developed systems in the categories of air-to-air, surface-to-air, air-to-surface, and surface-to-surface missiles. Missiles and other military weapon systems are important to deter war in critical times. But Douglas is not dedicated exclusively to defense projects. The name Douglas is synonymous with commercial aviation. The DC-6 and 7 series, mainstay of the world's airlines in the post-war years, carries millions of passengers and mountains of freight on regular schedules over oceans and continents. Airplanes of this type rank with the famous DC-3 as the most successful commercial aircraft ever manufactured. The production of modern aircraft and missiles entails many complex engineering and manufacturing procedures. An airplane like the DC-8 is the result of great vision, long experience, and hard work. At this point, I would like all of you to see some of the many methods that are followed when a Douglas product like the DC-8 is produced. It all begins with engineering, where design specifications for each separate detail of every new airplane are worked out. When the design engineering is completed, ideas only exist on paper. There's a long way to go until the paper ideas are turned into a fleet of jet transports. Production activity actually begins on the airplane when a schedule is established. Delivery dates determine the ordering of raw materials, purchasing of parts and tools, as well as controlling the rate of fabrication and assembly. We organize to have a production flow, a steady river of materials. The purchasing department goes into action and determines what is needed from blueprints and schedules. These orders materialize into carloads and carloads of parts, metal and rivets, lights and fabric, castings and forgings, electrical wire, steel wire, all of the 1,001 items that comprise an airplane. Before these items can be used, however, there is still more paperwork to be done. The highly trained men in the planning department decide how, where, and in what order each unit is to be fabricated and assembled. In addition, they determine the type of tooling required. Tool designers work out highly accurate dies, jigs, and fixtures. Making the tools is a precision job. In some cases, tolerances as close as 1/10,000th of an inch are required. Many ingenious tooling devices, like these plaster patterns, simplify manufacturing problems. Proven tooling techniques are used at Douglas, but in addition, new tooling methods are continuously being developed in our shops. With materials and tools on hand, it's time for manufacturing to take over. The function of production control has been described as having the right part at the right place at the right time. Production control regulates and controls the workflow through all manufacturing processes, from initial supply of materials to the fabricating department, through all phases of production, inspection, processing, sub-assembly, major assembly, installation, and final assembly. This responsibility ends. Fabrication of detail parts begins in the machine shops, where they are milled in precision machines, turned on various types of lathes, and drilled to meet exacting blueprint specifications. Routers carve the outlines of essential sections. Huge gantry cranes move heavy dies from storage points to working areas. Some parts of an airplane are formed by giant hydro presses, others by punch presses. Many sheet metal operations require hand forming, while in others, complicated stretch presses are used. This one, built for the DC-8, is the biggest press of its kind in the world. Operations at the burring bench remove rough edges from the fabricated parts. To protect parts from deterioration, many are processed in various chemical solutions. All the time manufacturing is in progress, maintenance men work steadily to keep machines in good repair. When a detailed part is completed and scrupulously inspected, it is ready to be delivered for assembly. The transportation department, ever mindful of schedule, delivers these parts to the assembly section, where they are stored in cribs and racks. An important skill in sub-assembly is welding. Welding by hand and by machine. Riveting is another valuable technique used in sub-assembly. Hand riveting done automatically. While all this is happening, the accounting and tabulating departments are keeping track of labor and material costs. Accounting is important, since it supplies vital information on how production stands in relation to men, materials, parts, schedules, and finances. Major assembly of a Douglas product, like a DC-8, begins when all sub-assemblies are ready to be combined. Most large sections are put together with the aid of huge jigs and fixtures. Electricians connect a maze of wiring. Constant inspection makes certain that every part meets exacting specifications.
Production rolls along to the point of final assembly, where wings and fuselage are joined, where the separate and detailed jobs of many Douglas employees combine to change the ideas that were outlined on the engineer's drafting board into a three-dimensional reality. Production procedure is much the same at all Douglas plants. Whether the finished product is one of our massive ballistic missiles, like the Thor IRBM, the dependable workhorse of the space age, produced by the Santa Monica Division, a sleek, graceful queen of huge Air Force cargo carrier from the Long Beach Division, a powerful jet bomber for the Air Force from our Tulsa Division's Modification Center, an accurate anti-aircraft missile like the reliable Nike Hercules with its atomic punch produced for the Army by the Charlotte Division, or swift and versatile new wings for the Navy from the El Segundo Division. These are not just airplanes and missiles, but Douglas products, built in the dependable Douglas tradition, with no compromise in integrity of design or workmanship. These vehicles of the air are a tribute to the men and women of Douglas who build them.
On the job, each employee has the protection of the best in safety equipment, which has resulted in one of the finest safety records in all of industry. A fine employee benefit program, including a comprehensive insurance plan, is available to protect employees and their families. Life insurance is provided to give additional security for dependents. Douglas has in effect a pension program, which is a real help in making plans for retirement. The Douglas Welfare Store is convenient and cooperative in helping the employee buy clothing, appliances, or gifts at Christmas. Employees can borrow money through the services of the credit union to fix up a home or buy a car at the lowest possible rates of interest. In addition to raises in pay, good work is recognized by promotion into better classifications and supervisory positions. And employee suggestions are welcomed and, if accepted, are rewarded with cash. Employees receive paid holidays and vacations and enjoy a full program of organized recreational events. Convenient to California. Well, that gives you some idea of what we do and how we do it. I've enjoyed this opportunity of talking with you about the company. We'll be looking forward to seeing you on the job.
Teamwork is essential in our business. Each one of us doing our job to the best of our abilities helps produce the world's finest airplanes and missiles. And that is the Douglas secret, a fairly simple one if you come right down to it. We take good tools, put them in the hands of good employees, and come out with a really superior product. Welcome to Douglas.